Okay, Assalamualaikum warahmatullahi wabarakatuh and good day to all. So we continue our lecture for chapter 1 transmission line theory. As all already know that we have 3 weeks to complete the transmission line theory part 1. No, chapter 1, and each of the week we divided the chapter 1 into 3 parts. Okay, part 1 is concentrated on the mathematical calculations, all the formulas related to the transmission line. In the second part is how we evaluate the transmission line using the Smith chart. The first one is how we evaluate the transmission line using mathematical calculations. The second one, Smith chart, and the third one is how we are going to make our load match with our transmission line. So we have to introduce the impedance matching. Okay. Then we go into our slide. Previously we stopped at this example 1.1, where in this example you need to calculate the characteristic impedance of the line given the value of RLGC and the propagation constant. You have to know about how to do these complex operations, square root of multiplication or square root of division. Okay. So before we go further, I would like to go into the big picture of this part 1. So we can go into this. I already make it as a summary for the part 1. What you already learned and what you're going to learn in part 1. Okay, so the summary here. We already go through the equivalent circuit. Okay, this is the transmission line example. So chapter 1 is about the transmission line. So this is the examples of the transmission line. Any of this transmission line, first of all is you have to know on how to convert it into the equivalent circuit and what is the label of that equivalent circuit. So this is the equivalent circuit of the transmission line. So we have the resistance, inductance, shunt resistance, and the capacitance. Okay, so this is usually a lossy transmission line, meaning that this transmission line has a loss. So how do you know whether this transmission line has a loss or not? Because it has the resistance and also the shunt resistance. Okay, it has R and G. So meaning that when a signal going through this transmission line, because it has resistance, so it will make your signal attenuated. So this is what we call as a lossy transmission line. Okay, so from this circuit diagram you can determine 2 parameters, which is the propagation constant with the alpha symbols and the characteristic impedance Z0, normally known as a Z0, meaning that your transmission line will have the impedance. Okay, now after you know the lossy characteristic of your transmission line, either propagation constants or characteristic impedance, then we can simplify this transmission line by assuming it is lossless, meaning that it is ideal, there is no resistance. Okay, so this is the formula of the alpha propagation constant and the formula of the characteristic impedance. This propagation constant will describe about how much attenuations that will be occur when going through this transmission line, which is known as alpha. Okay, so the propagation constant will describe your transmission lines in terms of attenuations and in terms of the phase constant. Okay, characteristic impedance is just describe your define your impedance of that line. So but we call it as a characteristic impedance Z0. And then we can consider ideal cases where we can assume that transmission line have no loss, meaning that there is no resistor in that transmission lines, meaning that the attenuations is 0. There is no attenuations, so that we can we can easily calculate certain parameter. This one is ideal case, definitely will not happen in the practical world, but to simplify our calculation, we can assume the resistance and the shunt resistance is negligible, meaning that it's can be it's very very low, so that we can assume there is no attenuations. Okay, when there is no attenuations, alpha is equal to 0, so your formula now is simplified like this. Characteristic impedance only L and C. Same thing with this beta and propagation constants. Okay, after that, previously we just consider transmission line, no connection at both end, at the input side and output side. When now when we terminate, meaning that we connect at the end of the transmission line with another load, so we have to evaluate the performance of that connections. So it can be evaluated in terms of the reflection coefficients, return loss, voltage standing wave ratio, VSWR, and input impedance. Okay, so this is the formula: reflection coefficient, VSWR, return loss, and also the input impedance. Okay, I will explain in details about this one at here. Okay, we know that any transmission line can be represented in terms of the two conductor wire like this. Okay, with the certain length. Transmission line, definitely it has a length, certain length. Okay, we already know the equivalent circuit. From this equivalent circuit, we can identify the value of the characteristic impedance Z0 and the value of the propagation constant, where this propagation constant can define the attenuations, Nipper per meter, the unit is Nipper per meter, and the phase constant. Okay, so that what is the for lossy condition. Lossless, when resistance and G is equal to 0, our attenuation is equal to 0. So this is the formula, Z0 and also propagation constant. Okay, this is when you only have transmission line without any connections. Now we put, okay, now here at this condition, you have this transmission line is connected to the load. Now when it is connected to the load and you are connected to the signal source, what happens is that you will have incident wave in forward wave and reflected wave in the in the reverse direction. Okay, so this evaluation is, we want to see whether our how much our signal can be transmitted until at the end of the load. So we have to evaluate the performance of the transmission line to see the matching performance. When we put the load to at the end of the transmission line, which has a Z0, so we want to see the matching conditions of this connection. Okay, so how we are going to evaluate the match condition? What does it mean by match? So matching meaning that, okay, match meaning that maximum power delivered to the load. That's match. If no matching at all, no power delivered to the load. So matching conditions meaning that it will give you the performance of your terminated transmission line with the load, whether your signal can go through this transmission line or not. If it is matched, all of your signal 100% is transmitted at the end of your transmission line. If it is not matched, what happen? it will be a certain of the power will be reflected back to the signal source. Okay, so how are we going to evaluate? We have like previously, we have reflection coefficient. So that is the formula. For example, here this is the circuit. The reflection coefficient is usually represented in terms of the magnitude and the phase. Okay, so it has a point, so meaning that the you can read the reflection coefficient, or you can give the value of reflection coefficient at any point, of your length. Okay, of your length. If you calculate it, ZL minus Z naught over ZL plus Z naught, you will get at any point, any length, you will get the same magnitude, only the phase is different. So either you go at the beginning of the length or at the end of the length, the magnitude will be the same. Okay, so the value here, the range will be from higher than 0, lower than 1. If reflection coefficient, the magnitude is 0, meaning that it is matched, so all the power is delivered to the load. If it is equal to 1, it is the worst case where it not match at all, so no power delivered to the load. So that's how we evaluate from the value of the reflection coefficient. You got 0, meaning that your load impedance is really matched with your transmission line characteristic impedance. If equal to 1, it is worst case that not matched at all. If between 0 and 1, there is a percentage that certain power is reflected back to the signal source. Okay, second one, okay, this one is unitless. For the reflection coefficient is unitless. For the return loss, it's represented in dB, so just related to the magnitude of the reflection coefficient. So also here you can know, if it is the value is infinity, it is matched. If it's 0, worst case, all the signal reflected. Another way to evaluate the performance of the transmission line is the VSWR. Also, the value is related to the reflection coefficient. The VSWR, the range is higher than 1, lower than infinity. If it is matched, VSWR is equal to 1. Okay, another one is input impedance. Okay, why this input impedance is important is because most of the time, definitely, your load impedance will not be matched with your characteristic impedance, Z0. ZL will not be equal to Z0. That is the practical case happen in this world. Okay, definitely you cannot get load equal to the characteristic impedance. Okay, so what happened is that you have to know how to calculate the input impedance, because by knowing the input impedance, later you can introduce a matching network to make your characteristic impedance match with your load. So that's why we have to know how to calculate the Z-in at certain length. Okay, so this is the formula. I think you can just simply if the values are given, ZL is given, Z0 is given, length is given, then you can simply put in the formula and calculate. So that's all the important parameter that you have to know in this chapter 1 part 1. Okay, so firstly is about the circuit. From that equivalent circuit, you can get the characteristic impedance and also the propagation constant. Why you have to know that characteristic impedance Z0 is because of, you see here, the Z0 here will be useful for you to calculate these parameters. Reflection coefficient, when you know the reflection coefficient value, you can calculate the return loss, you can calculate the VSWR, and also you can calculate the Z-in, if you know the Z0. That's why the first thing that you have to know is the equivalent circuit. From that equivalent circuit, you can calculate the Z0. And propagation constant, because in that propagation constant, you can know what is the value of the attenuations of the transmission line. Okay. So after you know this equivalent circuit, how to get the values of Z0, how to get the values of the propagation constant, then you can connect your transmission line into any load at the end of your transmission line. So you can connect transmission line with the load impedance. But what happens when you connect your transmission line with the load impedance, Z0 with the ZL, it will give you certain performance of the reflection, because if Z0 is not equal to ZL, meaning it is not matched, so it will introduce a reflection to your signal source. Okay, so what does it mean by reflection? Meaning that not all of your signal are transmitted to the end of the transmission line. So you should be like, have to evaluate whether the load will make how many reflections when connected to the Z0. So how you are going to evaluate that? There are three parameters: reflection coefficient, return loss, and VSWR. Zin is for you to know, so that you can see how much is the mismatch. Then from the values of the Zn, you can use this one letter to design your matching network. So in the slides, there are examples. We already go through example 1.1, where in this example, it gives you the values of your equivalent circuit, the lump components of equivalent circuit, for you to calculate the characteristic impedance and propagation constants. The question is very straightforward. You just substitute all the values, but you have to know on how to press on your calculator. If you have division, just divide the magnitude. The phase, you have to minus and divide by 2, because it is square root. And for the multiplication, the phase you have to plus both, add both and divide by 2 because of the square root. So you have to know how to convert to Cartesian, how to polar fault, and how to do the complex number operation. Okay. Second question. Okay. The second question, example 1.2, is similar to example 1.1. It's just at this example, you have to compare the values of the characteristic impedance and the propagation constant between lossy and lossless condition. So this one also very straightforward. As long as you know how to press your calculator, how to do the complex number operation, then you can follow this. That one is lossy condition. At the lossless condition, alpha is equal to 0. So you can simplify the formula, the previous formula, you got this one. So it is very straightforward. Okay. Example 1.3. Example 1.3 is just to calculate VSWR, reflection coefficient, the magnitude of reflection coefficient, and the return loss. Also this one very straightforward. Any of the value is given, as long as you use the correct formula and you know how to press your calculator, then you can get all this answer. Okay. And last one is how to calculate the Zin. Okay. This question, a source with 50 ohm source impedance drive a 50 ohm transmission line that is 1/8 of wavelength long, terminated in a load ZL is equal to 50 minus J25. Calculate reflection coefficient. You see here, reflection coefficient gamma, there's a L here, subscript L, meaning that you want to calculate the reflection coefficient at the load. Okay. Second, VSWR. Third, Zin, seen by the source. Okay. So first of all, just convert these sentences into graphical representations. Okay, so this is Z naught. Okay, Z naught is given. So here Z naught is given 50 ohm transmission line. So that is your Z naught. Okay, then you have 50 ohm source impedance. Source impedance is this one, which is next to your signal source. You have the length of 1/8 lambda. 1/8 lambda. Okay, and then you have the load impedance 50 minus J25. So that is 50 minus J25. So when you have these graphical representations, then you can do the calculation. So this is the formula. It's very straightforward. Just substitute the value of load impedance and your load characteristic impedance Z0. Substitute, you got the answer. And don't forget to, okay, you see here the formula is in terms of Cartesian, where you have X and YJ. Okay, but don't leave the reflection coefficient value in X and YJ. You have to convert it into magnitude and phase. Okay, you have to convert into magnitude and phase, because in the reflection coefficient you want to know what is the value in terms of the magnitude. If you leave it in the Cartesian, you cannot know what is the magnitude, because from the magnitude previously, you see here, from the magnitude itself, either it is 0 or 1. From 0 to 1, you know whether your load it's giving reflection or not. Okay, so that's why we want to know the magnitude. And here you have to leave your answer in terms of magnitude and phase. Okay, also when you know what is the magnitude, you can use that value to calculate the VSWR here, and also to calculate the return loss. So that's why you have to leave it in terms of magnitude and phase. Okay, and then lastly is the input impedance. So just substitute the values. So we have length is equal to lambda over 8. Okay, beta is equal to 2 pi over lambda. You can cancel out the lambda, then you got tangent pi over 4. Okay, tangent pi over 4. Substitute in this equation, then you get the Z in. And usually Z in, just leave it in X and Y J form, Cartesian form, because because in impedance usually it is given in terms of X and Y instead of magnitude. So that's all for this chapter 1. Chapter 1 part 1 is all about the formula. You see, all about the formula. Later in the part 2, we will see all this reflection coefficient, return loss, VSWR, input impedance using Smith chart. So that's all for chapter 1 part 1. Okay, thank you.